confirm that you can see the cursor moving?
Yes, it's moving.
Okay, great. So hello everybody. I am Swagata Mukherjee from IIT Kanpur. And in this preschool, I actually plan to give total 2 talks. So one is today, which is on basics of deep learning. And in this talk, I will assume that you have very little to no prior experience of deep learning. So that basically means that I will start from easy things and then build up on top of that and try to explain the details of deep learning. And then I guess the plan is that tomorrow I will, in the same slot, I will give another talk, which will cover the basics of CNN. And basically, tomorrow we will start from the place where we will stop today, and then we will continue and try to reach until CNN. So the term deep learning, so the term deep learning actually refers to training of neural networks. And in this talk, we will see what exactly is a neural network. Let's take a very easy example of housing price prediction. Let's say we have a data set of 6 houses and the size of the houses are given to us and the price of those houses are also given to us. And if we plot that, so if we plot size in x-axis and price in y-axis, we get a plot like this, as you can see in the left. And you can probably fit a straight line, but if you just fit a straight line, then at some point the straight line crosses this x-axis, which means that the price becomes negative, which is unphysical. So that is why we have plotted it like this. So it's a straight line, and then as soon as it tries to cross the x-axis, we don't go further. We just draw a horizontal line here. So this, what we have been doing here for this very simple case, you can think of it as the simplest possible neural network. This has a neuron and it takes one input, which is size of a house. And this input, any input is generally termed as X. And then this neuron does this fitting, which is mostly a straight line fit. And then what it gives is the output, which is the price here. And we generally denote the output as Y. So it has, this is not a neural network per se, it is just one neuron. Now, the function that you see here, this is a very common function in deep learning, as we will see in the next slide. This is actually called ReLU, or rectified linear unit. Rectified just means that here we are taking a max with 0. So we are not letting it to take any negative values. That's all it means. Okay, so now that was a very easy example. Let's make it a little bit more complex, and so that we can view a slightly bigger neural network. So we stick to the similar example of housing price prediction, but now instead of only one input variable, size, we have 4 input variables: size, number of bedrooms, postal code, and general wealth of the neighborhood place. And we have, after the input layer, we have this one layer which takes these input variables, and let's say it computes something. And let's try to visualize or think what these 3 nodes might be trying to compute. So let's say the first node mostly relies on the first two variables, size and bedroom, and it tries to compute how big of a family size this house can accommodate. So that will depend on the size of the house and the number of the bedrooms. The next node, that is this one, let's say it takes the postal code of the house, which is related to the location of the house, and it tries to predict the walkability of the neighborhood. And the last node or the third node, let's say it takes the postal code and the general wealth of the neighborhood and tries to compute cleanliness of the general neighborhood. And these three factors are something that can influence the price of a house. So family size that it can accommodate, walkability of the neighborhood, and cleanliness of the neighborhood. So this goes to another node, which is the output layer, which has only one node in this case, and this predicts the output. So you already see that there is a difference between the previous case and this case, because this case has this one additional layer. And as I was saying, that the first layer, we actually do not count it as a layer. So let's call it layer 0. This is the input or X. And then this layer, this is actually called a hidden layer. And these nodes or circles here that you see, these are called hidden units. And this is the output layer, which in this case is just only one node. So the magic of the neural network is that you will provide X and Y. So you will provide the values of these variables that are given here, and you will also provide the value for price and all the other things which are happening in this hidden layer. The neural network will be able to figure these things out itself. So what we actually implement is something like this. So instead of deciding that the first node will take input only from first two input and it will be calculating something related to family size, and the second one is walkability, rather than deciding these ourselves, what we do actually is that we give all the four inputs to all the three units of this hidden layer. So everything is connected to everything else. This is also called fully connected. And then we don't care anymore what these units are actually learning or actually computing. We totally leave it on the neural network. It computes whatever it wants to compute. It learns whatever it wants to learn, and then it outputs the Y. So since all the inputs are connected to all the hidden units, this has a name. It's called fully connected or densely connected. And the type of problem that we are discussing here is called supervised learning, which means that labeled data is available for training this model. Labeled data meaning that the actual output is already provided, and the values of each input, x1, x2, x3, x4 in this case, they are also provided. And then when the model is fully trained, which means that in our very simple example, let's say here, so model being trained means you have this fit function. Then if someone comes up with a new house with new input features, in this case, there was only one, then one will be able to predict the price. So that is the idea. Okay. Now, the kind of
I have a question. So
yes.
in the previous image, you have shown that the rectified linear fit. Yeah, so yeah. So it this model can do a extrapolate this kind of thing because we have a no data near zero price, right?
Yes, so this is also not a very physical thing to do, because we have here finite size of house and price being 0, which is not a very good idea to do. So this was a very simple example, which is still at this region very unphysical.
I think near or near sites of houses, we have no data in this region as well, right?
Yes,
And
yes.
just so this model can do a extrapolate this kind of things. So we know only interpolate. So we have a data and intermediate some point we know the price we have to price it and then
Yes.
but
Yes,
it can do a extrapolate this kind of things.
no, we cannot, because we have no idea of what is happening here. So this was a very simple example to introduce the word ReLU early on.
Okay.
All right. So now the kind of problem that we just discussed, which was housing price prediction, this is also called regression problem because here the output is a continuous value of something, in this case price. But oftentimes we also do classification kind of problem, and that is something we will discuss next. So before moving on, I just wanted to mention that there are two kinds of data which one will encounter in machine learning problems. One is structured data, where you have some input variables whose values are given. So in the left-hand side, you just see the problem that we just discussed here. So the data is available in a tabular form like this. And there can also be unstructured data. For example, an image or an audio clip will be examples of unstructured data, where you can still write it in a tabular form, but you have to do some work to go from here to here. So we will discuss that later. And before moving on to the technicalities, there are a few things that I wanted to discuss. For example, one is where you can expect improvement going from traditional machine learning or the older era machine learning things from the very new generation things. So we will be discussing in the course of this course many different machine learning algorithms, and one might get confused about which one to use where and things like that. So this is something I thought will be good to discuss here. So let's say, so there are two things here. One is the amount of data that you have, and the complexity of the neural network, that is how big your architecture is. And the general notion here is that the scale drives the deep learning progress, and the scale here is the scale of the amount of data and scale of the largeness of your architecture. So if you have small amount of data available to train your network, then
Excuse me, ma'am.
yes.
Ma'am, what do you mean by architecture?
So architecture would be this. So the way you have designed your network. So how many hidden layers you have, how many hidden links you have. So this whole thing is called architecture.
Okay, ma'am.
Yeah, basically you can also say that it's a network. And so the thing here is that if you have small training sets, then all these neural networks, so large, medium, small, and more traditional learning algorithms like logistic regression, which a little bit old and nowadays not used too often. But in the regime of small training set, they kind of all work similarly. So the performance-wise, maybe a larger neural network will give you a very slight performance boost, but not a whole lot. But as you increase your amount of data, as you accumulate more and more data, so you are training your network with a huge amount of data, then you will see how the power of a large neural network shows up. And in that case, what we generally see is that traditional learning algorithm, their performance plateaus at some point. They do not increase anymore with the amount of data. the small sized neural net, their performance increase slowly and then it plateaus at some point again. Same for medium sized, and for the large neural network, the performance seem to increase with the amount of data. So when you have a huge amount of data, it is probably best to use a large neural network, assuming that you have the computing facility available to do that. So more
So I have
data.
a question. So in the previous slides, so when you train the model, so is there some parameters or it's
Yes, so there are actually a lot of parameters, and there are two kinds of parameters that we will be discussing in the next slides. One is called parameter, and one is called hyperparameter, and all of those needs to be tuned in order to get the best performance. So we will discuss that in detail.
so in that two cases, the parameters of these models are same. We are training with the same parameters
No.
with a or different parameters.
The larger the model, you will have more and more parameters, and that is why the model is more and more flexible and it can learn more complex things. So in order, yeah, if you, I mean, if your data has very complex patterns, then with small number of parameters, it is probably not possible for the neural net to learn those complex patterns, but a large neural net can figure it out because it has a lot of flexibility in the form
Okay,
of.
So that means the amount of data increases, we will need more parameters to, and that's why this gives a better results.
Yes, yes, exactly. Large neural net also means a large number of trainable parameters. Yeah,
Okay.
so we will just get into that. So yes, so more data is important, more computing power is important, and of course, innovation of algorithm. This is something you will see during the course of this preschool and also main school, how many algorithms came up, and how people improved those algorithms over time. One thing to note is that the process of training a neural network is oftentimes a very iterative process and an empirical process. So let's say you have a problem in hand and you have an idea how your network should look like, and you implement that idea, you run it and check the performance. Let's say you are not very happy with the performance, so you go on and you have some more idea to how to change things. Again, implement that change, again check and repeat. So this is how it generally goes. So since it is such an iterative process, it is very important to be able to run the training of a network very quickly, because if every iteration of this takes a long time, that is not very efficient. So it is important while you are writing the code to implement a neural network to keep in mind that to write the code in a way that it runs fast. And in this context, we will discuss something called vectorization, which makes your code run fast. We will discuss. Okay, so again, we will start our discussion with a simple network called logistic regression. And there are many ideas or many intricate details of logistic regression, which is exactly same as neural networks. So we will learn all these ideas using this simple example of logistic regression, and then we will apply that on neural networks. So it is always easy to discuss things using a simple example to get the intuitions correctly, rather than trying to learn it with a very complex example. Then intuitions gets lost a little bit in the technicality. So that is why we are starting with the simplest possible neural network, which is also called a logistic regression. Okay, so coming to the notations. So for logistic regression, it is mostly the binary classification problem where we use logistic regression. And binary classification means, for example, you are given a picture of something and you have to say if it is a cat or not. So this is a very common example that is given in machine learning literature. So cat classification. So notation wise, XY is a single training example. X is input and Y is output. Now, X, as we discussed before, X can have many variables or many features. So X1, X2, X3, X4. So X, when we say X, it is actually a n-dimensional vector. It's called a feature vector or an input vector. And Y, since it's a classification problem, so classification is basically yes, no kind of problem. So Y is either 0 or 1. So let's say we have a big data set with m number of entries. We will use m as to denote the number of entries in a training data set. And generally we write x subscript 1 as a column vector with n entries. So which means that this is the first entry in our training data set. And this is a column vector, and it has entries of the column vectors are the different features. So then we can write these column vectors one after the other. So x1 is a column vector, x2 is a column vector. So we stack them up one after the other, and then what we get out of it is a n cross m matrix. So n is the number of rows, which is also the number of features. M is the number of columns, which is also the number of entries in the training data set. And this n cross m matrix is our whole input matrix. And one of the things that becomes a little bit problematic when you code this up, when you write the code in Python, the most common error that people get while writing this kind of code is related to the dimension of the matrix. So it's a good idea to check the shape of the matrix when you are implementing these things. And Y, in a similar way, just like we defined capital X by stacking up the small x for all the entries, similarly, we can do exact same thing for Y. Y will be a 1 cross M matrix, M because we have M examples in the training set, and 1 because Y1, Y2, these are just numbers, 0 or 1. So as I was saying, that it is very important to write the code in a way that your training is very fast. If your training is fast, you will be able to check many different permutations and combinations of your the choices that you have, and we will discuss what choices you will have. So basically the choices are choices of hyperparameters. And a priori, it is not known what will work best. So that is why these iterations are needed. So one has to run the training very fast. One way is to avoid using explicit for loop. Wherever you can avoid explicit for loop, please avoid that. Because when you have an explicit for loop, it generally slows down the performance of the code. The runtime-wise performance of the code. And also another thing is that the things that we will
So that's why we do vectorize this kind of things
yes,
instead of for loop.
Exactly. That is
I
why we do the vectorization. Then if you run a for loop code and a vectorized code side by side and check the time it is taking, you will see that oftentimes it is 1 order of magnitude or even multiple orders of magnitude faster with the vectorization. So one thing is that we will be discussing many basic concepts in this lecture, but many of them actually are already implemented in different libraries, and they are all available in something called TensorFlow, which there will be, I believe, a tutorial today So in general, it is not needed to implement these algorithms by hand because they are all implemented already and available for your use. But for your own understanding, if you want to implement it at least once to see that this really works, that is also not a bad idea. You can do that, let's say, the time that you will have between the preschool and main school, you can try some of these things out. Okay, now let's say we will write our binary classifier. We have an input image, in this case, this one, a cat, and the binary classifier output is 1 or 0, so cat versus non-cat. So how does the computer see an image? So what it sees is actually 3 matrices, and these 3 matrices are the pixel intensity values. And 3 because this is a colored picture, so there will be red, green, and blue, these 3 matrices. The size of the matrices, of course, will vary. What I have shown here is a very, very small matrix. Generally, it's not this small, it's much bigger than this. And each element here is a feature. So we need to unroll all of this in the form of a column vector that will be small x subscript 1 according to our notation. So you can imagine that it will be a very long column vector, especially if the input image is high resolution. Let's say we have an input image which is 64 by 64, then the number of features will be 64 times 64 times 3, which is this big number 1, 2, 3, 8, 8. So our small n number of features is very high in this case. So this is one of the reasons why when it comes to problems related to an image, we generally do not go for logistic regression or neural network or deep neural network. We generally go for something called convolutional neural network, which is something we will be discussing maybe tomorrow. But this is the possibility.
In the previous slide, I am not understood. What are the 3 matrices?
So these are the pixel intensity value. Let's say in this picture, there are pixels everywhere, and every pixel has an intensity value. That is how you create the contrast between the background and
Basically, RGB values for each point.
yes, exactly, the intensities. So this is what the computer sees. Of course, the computer cannot see what we see, right? It just sees a bunch of numbers, and these are the intensities.
But here, so there's a square matrix. Is always be a square matrix, or it depends on when each point.
This is not a square matrix, right? This is like 4 numbers here and 5
Oh,
numbers.
I see.
Yeah.
It's not necessarily a square matrix.
Not necessarily square matrix, although in most cases, we try to use a square matrix if possible. You can always add a bunch of zeros to make it a square matrix. Bunch of zero would basically mean nothing. It doesn't affect the information that you have in the image, but makes your non-square matrix a square matrix. You can do that. Okay, then yes. So so moving on to next slide. So given an input, we want a prediction, which is generally called y hat. So the true output is y, and the predicted output of the network, in this case a logistic regression, let's say, it is y hat. And we always want our predictions to be correct. That means that we want y hat to be very, very close to y. So the parameters, so speaking of the parameters and answering the question, so the parameters that we have is generally called W and P. This is what we generally use in the deep learning literature. You can also call it basically anything, but it is called W and P, W for weights and B for bias. This is how it came. And W is a vector, and how its dimension would be something we will discuss in detail. And B is a real number. So for logistic regression, so let's say we have a few W's here. We can say W1 x1 plus W2 x2. If we have only two input features, x1 and x2, then for one training example, we will write W1 x1 plus W2 x2 plus B. So the easy or compact way to write this is W transpose X plus B. So you can just multiply the vector X and this vector W, but you need to have a transpose here for this multiplication to work. And in logistic regression, what we do is that in any machine learning problem, what you need is an activation function for non-linear. So in this case, it is a sigmoid. So what it finally does is that the predicted output y hat would be a non-linearity or activation function, in this case sigmoid, but there are other possibilities also, applied on this linear thing that is written here, which is parameter matrix multiplied by input features plus a real number. The sigmoid function looks like as it is drawn here. So if it is a sigmoid of x, then x is plotted here in the x-axis and sigmoid is plotted in the y-axis. And this is a function whose values remain between 0 and 1. And if x is a very high value or if x is a very small value, then it approaches these asymptotes. Otherwise, in the middle part, it is mostly linear. So now we understand that we have some parameters, and in order for the network to predict something meaningful, these parameter values have to be learned. And for that, we need something called cost function, which will help the network to learn these parameters. And now we will discuss how that can happen. So basically,
in the previous slides, so this y have two values, right? 0 and 1.
yes,
And here you are formally write that y hat y equals to 1 for x.
yes.
Or 0 of x, I mean, this thing, how do I do? Or just
Oh.
subtract or no?
So what happens is that the final value will be between 0 and 1. And this is like a probability. So we can say that if the value lies in this region, so 0.5 to 1, then we will say that it is predicting y equal to 1 or y hat equal to 1. So it is predicting that the picture was a cat picture. And this region less than 0.5, we can say that it is predicting 0. Y equal
How
to
do I get this form if x is 1 by 1 over, how do I get this form if x equals to 1 over 1 plus e to the power minus x?
So this is just a plot of 1 by 1 plus e to the power minus x. This is a form of the sigmoid function. This is how it looks like when you plot this function as a function of x.
Yeah, but how do I get this functions?
How do you?
How do I get these functions for a given?
Ma'am, I think what he's asking is if the sigmoid function is same for every time, or is it will be different for different cases.
Yeah,
No, it's the same for it depends, of course, on the value that you are providing. But the sigmoid function will always look like this. It is always, or will be predicting something between 0 and 1. Now, if you are saying that your x is 2, then it will predict something here. If you say the x is minus 4, it will predict something here. But the general form is like this.
But y have a two variable, 0 and 1.
Y have 2, that is what I'm saying, right? That y hat will be any value between 0 and 1. And then you can say that when y hat is above 0.5, you can say that it is predicting y as if it is predicting y equal to 1. And when it is, when it is less than 0.5, as if it is predicting that y is 0. So this is like a probability.
I see.
Okay, so then we will introduce two terms. One is loss function, and loss function is something that if your network gives you a wrong output, so if your y and y hat are very different, if they don't match, then loss function is something that will be able to capture that and will be penalizing because of that mistake. So it is written in a way, and you can convince yourself by just taking y equal to y hat and just compute this thing by taking y equal to y hat and y not equal to y hat. So then you will see that the loss function is written in a way that when y equal to 1 and y hat has predicted, let's say 0, which is a wrong prediction, then the loss function will not give its minimum value. And our idea is to minimize this kind of loss function. So minimization of the loss is what we are aiming for here. So loss function is carefully designed to capture whenever your network is predicting a wrong value. And cost function is just that you sum up the values of the losses for every training example that you have, and you have m of them. So at the end, you divide by m. So the loss function and cost function definitions are this, and we would like to find the parameters w and b that will minimize our cost function. So that is the end goal. That is how the network will learn the correct values of w and b. So the way it actually does that is something called gradient descent. So the algorithm by which this minimization takes place is called gradient descent. So basically what we have written here are the things that we have discussed before. So y hat is sigmoid applied on W transpose X plus B. We can write this thing as Z. Let's say W transpose X plus B is written as Z here. And cost function, which is J, function of W and B, is just this. This is also we just wrote in the last slide. So sum over the losses that you get from every training example and then divide by m, and this is the form of the loss function. So the idea is that you will initialize the values of w and b anywhere. It can be a random initialization, it can be initialization with 0. For logistic regression, initialization with 0 will work. For neural network, initialization of 0 does not work, and we will discuss why. This is just one of the differences between logistic regression and neural network. Otherwise, everything else that we are discussing, they also apply for neural network. So the idea is that, yeah.
So how do we get the loss and cost function? Why this particular form is come?
So the form is chosen, as I explained, in order to capture whenever there is a difference between y and y hat. So you can convince yourself by taking y equal to 1, y hat equal to 0, and see what is the loss function, what is the value of the loss function, and y equal to 1, y hat also equal to 1, and see what is the loss function. You'll see that loss function will give a smaller value when you are predicting correct things, and loss function will give a higher value when it is predicting a wrong thing. So there can be many ways you can write a loss function. This is being written because this is the one which is normally used for this kind of problems. People came up with this because this is a form that, first of all, the basic idea of capturing the problem, that is something it is satisfied by this form. Also, the computation wise, this is very fast.
So is it the empirical expression, or is there any proof of that? it is the most the form that can be useful for the uh, high physics or machine learning, or is it only getting by that empirical form? Mhm.
So most of the things here is empirical in the sense that this is not unique. There are many different kinds of loss functions that one can write. Those will also work. It's just that in order to minimize this loss function, one has to take derivatives of this loss function, as I will discuss just below here. And so that is a kind of computation that one has to do. We would like to have a loss function whose derivative computation is not time consuming. So that is one of the reasons this is chosen. So this is not unique because the thing that you are trying to capture in this loss function is just that when y and y hat differs, there should be a penalty factor that can be achieved by many different forms. So this is not unique, or it is not coming from any first principle. These kind of things are mostly empirical.
Something look like for a two-level systems are the Shannon entropy type things, right? So x log x and 1 minus x log. Is there any relations to that?
I'm not aware of any relation to that.
Okay.
So then we came up with this loss function and cost function. So our main idea here is that, so what is plotted here in this left plot is that the y-axis is the value of the cost function. And since this is a function of w and b, the w and b are these two axes, and you see this bowl kind of structure here. It will not always be taking this form, but this is one of the examples, which is a good example to take. It has a clear minima here. And you can initialize, and then the idea is that at every step of gradient descent, the algorithm will take a downhill step and will try to reach the minimum. At the minimum, there will be some value of w and some value of b, which is minimizing this function, and that value is something that will be taken or will be chosen. So this is an iterative process. After initializing, you will take this derivative, since you are trying to take a downhill step. So you will take a derivative of the cost function with respect to w. You will also take a derivative of cost function with respect to b. And then to go towards the minima, the idea is that you will replace, in every iteration, you will replace w by w minus alpha. I will discuss what is that. And then the derivatives that you have taken, same for b. Alpha is a hyperparameter. It is something that one has to tune, and it is called the learning rate, which basically means when you are going downhill, how long a step that you will take, whether you will try to take a very long step and go to the towards the minimum very quickly, or you will take very small steps and will take a long time to reach to the minimum. So both has its pros and cons. Sometimes if the value of learning rate is very high, instead of going towards the minima, it sometimes goes in a wrong direction. And if alpha is too small, then it also takes too long. So generally, that is why alpha is a hyperparameter whose proper value has to be found out. Okay, now moving on. Now, yeah.
So if alpha is small, then it will be more accurate, but it will be time consuming. Is that only the
Exactly.
drawback? Okay.
Exactly. Yes. If alpha is small, it's generally very accurate. It will steadily move towards the minimum value, but it will take a long time. So then yeah. Any other question? Okay, so Is there anybody who is unmuted? And hearing some echo. Okay, so for logistic regression and also for neural network, there are a few things that are important. One is called forward propagation. This is a term you will hear a lot if you read the literature of machine learning. And this just means, this is actually a very simple thing. So once you have your x1, x2, these features, and accordingly you will have w1, w2, and b, then the computation of z is just w1 x1 plus w2 x2 plus b, or w transpose x plus b, or that is z here, computation of that, and then applying the activation on z, which is let's say sigmoid in our case. And basically, that is the y hat in our simple example here. This is also sometimes called a, and in this case, y hat and a are the same thing. And then computing the loss from y hat and y. That is, so the going from these x and w's and b, going from left to right and computing loss. So that is the forward propagation. This whole thing, drawing it up like this, is also called a computation graph. And then backward propagation is computation of the derivatives. So in the last slide, I discussed that once you have computed the loss function and the cost function, you have to compute the derivatives and in an iterative way, try to go to the minimum. So that part is called the backward propagation, because now you are starting from the loss and then you are going as if towards the left. So this is for one training example, but you have multiple training examples. So in general, you have to either vectorize or write a loop. So this is how it generally looks like if you do it via a for loop, which is not recommended. So these are the initializations of your cost, and dw just means del j del w1. This is just the name of the variable dw1. Similarly, dw to db, they're all 0, and then you have the loop over training example, and this is what we would try to avoid. And then there is also a possible loop over the number of features. Here we have only 2, so that's why we have written those 2 by hand. But if n is large, maybe one would like to also write a loop here, but this is also avoidable. So now moving on to one example of vectorization, and this is an usage of NumPy, which I believe you already had a tutorial, so you probably already know, so I will go through it very quickly. So for one training example, you have W transpose X plus B. This computation needs to be done. So instead of doing it W1, X1 and W2, X2 in a loop, you can just do it in one go. If you have a full W vector with you and a full X feature vectors with you for one training example, then you can use NumPy dot this thing, and you can just multiply W transpose and X in one go for all the features all together, and then plus B. And one thing to note that while we would like to avoid for loops, but it will not be possible in all situations. For example, there is a for loop for number of iterations. So let me just go back and quickly show. So here in gradient descent, there is a number of iterations to be taken. So how many steps it will take to reach to the minimum. So that is the number of iterations. There will be a for loop associated to that, and this is generally something that is unavoidable. Okay, now moving on. Right, so this is the forward propagation for logistic regression, now written for first training example, second training example, and third training example. So this will be repeated m times. And recall that we defined our capital X matrix from our small x matrices by stacking them together. X1 was a column matrix, X2 was a column matrix, and stacking them, we got a n cross m matrix. Similarly, we can get capital Z by stacking one after another these small z matrices that we are computing like this, and then we just do this. So W transpose X, we just saw in the last slide how to do using NumPy, and then plus B. So of course, we should have a matrix of B, so B, 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 and repeated many times. However, note that there is a way of just writing only B, and Python broadcasting will figure it out that B has to be repeated m times in order for this summation to properly happen. So if you just write plus B as a real number, Python broadcasting is something that will figure that out under the hood. And then similarly, we can define capital A, which are small a's stacked together m times. And so sigmoid function will take Z. So Z can be a single valued function. It can also be a vector valued function. So that is something that is allowed in Python. So if you provide this capital Z, it will still be able to compute sigmoid for every small z. So this is how forward propagation can be written. Again, to remind you, all of this has already been implemented in TensorFlow, and nowadays nobody need to implement all of this by hand, but it is still good to know what is actually happening inside that black box before using that as a black box. So the back propagation in a similar way can be vectorized, and I don't think I'll be discussing that here. So moving on. So here we have now already discussed logistic regression, which looked like this. We had a few features, x1, x2, x3. It was being fed to a node, which was computing our z, and A was basically our y hat. And this is how the computation graph looked like if it was a logistic regression. Now let's discuss neural network. So neural network looks like this. We have the same x1, x2, x3 as input, but now instead of this only one node, we first have one layer with multiple nodes, in this case 3, and then we have another node. This is the node similar to the logistic regression, which gives out the y hat. And so the first layer here, so recall that we don't call input layer as layer 1, we call input layer as layer 0. So the layer 1 is this first hidden layer, and this will compute. Now we will not call it Z and A, we will call it Z1 and A1. So to make sure that these are associated with layer 1. And then the next layer, which has only one node, this now computes Z2 and A2. So you can see the pattern here, that this is basically doing exactly the same thing, same kind of computation, but repeated many times. That is the only difference between logistic regression and neural network. Otherwise, all the ideas of forward propagation, back propagation, gradient descent, and sigmoid function, all the ideas, they are the same between logistic regression and neural network. So this is how it goes then. X, W1 and B1, you compute Z1, then you compute A1, then you, at the end of layer 1 and beginning of layer 2, you would need 2 more parameters which are associated with layer 2. So that are fed. So Z2 is computed, A2 is computed, and then you have the loss, because A2 here is essentially the y hat.
The parameter W and so the parameters W and B are fixed by layer or node? It's fixed by layer, right?
So both, right? W parameter is it's actually a matrix. It's not one value. W is a matrix.
Yes, W is a
And
matrix.
yes, so it will. I actually have a dedicated slide on this. So just wait a little bit, and
Okay.
we will discuss about what will be the dimension of W matrix for every given layer of a neural network. And you will see that it will depend on the number of nodes that you have in that layer and the number of activations coming from the previous layer. These are the two driving factors. Okay.
So, ma'am, in the forward logistic regression, we just find the loss function.
Yes, the forward propagation is just finding the loss function.
Okay, ma'am.
All right. So now, right. Okay. So this is actually the slide that I was talking about, where we have a short discussion about the parameters. So the input layer, we have the X here, and X also oftentimes is called A0. And then the so not the second layer, the first hidden layer, which is layer 1. In this layer, A1 is computed, and then we have A2 in the next layer, and Y hat is A2 in this particular neural network. So the parameters associated with layer 1, so that will be W1. In this case, that will be a 4x3 matrix. 4 because we have 4 units in this hidden layer. So I'm talking about this layer, which has 4 units. 4 cross 3 because the layer before that, we have 3 inputs coming from here. So you can take it, think of it as A0. And for B1, so B or the bias values for this layer, it will be a 4 cross 1 matrix. This is 4 because we have 4 nodes, and this is just one value. Similarly, the W2 will be a 1 cross 4 matrix here because one node here and 4 A1s coming from here, and B2 will be a 1 cross 1 matrix. So as I was saying before, that what neural network does is actually very similar to logistic regression, but repeated multiple times. And you can, again, for neural network also, you can do a vectorized implementation of the forward propagation and back propagation. And it is even more important to do it in a vectorized way because now the complexity is increasing. And if you want to do it with multiple for loops nested within each other, it will actually take even more time. So vectorization is more important here. Okay, now, okay, moving on. So here, this is the forward propagation for a neural network with one training example. For one training example, I guess I have already shown this using a computation graph, but if you just write the equations one after other, this is how it looks like. So Z1, W1x plus B1, then you apply sigmoid on Z1 and get A1. And then in the next layer, you compute Z2. So that will be W2 A1 and then plus B2. And then you apply sigmoid or any activation on Z2 and you get A2. And A2 is Y hat. Once you have obtained A2, you are ready to compute the loss. And for M training examples, we should vectorize, and this is written in a for loop way, and this is exactly what we would like to avoid. So in the similar way that we did for logistic regression, this part can be vectorized. Okay.
So, ma'am,
Now,
can we do like we have done for the 2 step A1 and A2? Can we move forward like A1, A2, A3, and A4? Why
absolutely.
there is?
So here we have to stop at A2 because after the second layer, there is no other layer. That is why we are stopping at A2. Now, for more complex neural networks, you will have more layers, and accordingly, you will have A3, A4, and other layers.
Okay.
So now, speaking of activation function, we have only talked about sigmoid so far, but there are actually better options too. Sometimes the tan hyperbolic, actually almost always tan hyperbolic works better than sigmoid in the hidden layers. This has something to do with the fact that for tan h, it is going from -1 to +1. This green one is tan h. So the shape, roughly, the shape is similar, but the range is different. And oftentimes for the feature vectors, we normalize the feature vectors in a way that they should cluster around 0. I will discuss the normalization of feature vectors later on. And the fact that the middle point of tan h is at 0, this sometimes seems to help. So tan h you will see a lot. And then another thing is that sigmoid and tan hyperbolic, they both have one issue. So we apply these activation functions on z. And let's say, so this is it. So we compute z and then sigmoid on z or tan h on z. So let's say your z is a very high value. Let's say that means that you will be operating in this region that is almost becoming asymptotic. So the problem that happens is that if you are operating in this region where the slope is close to 0, then gradient descent becomes very slow because eventually you will have to take derivative, and based on the value of the derivative, we'll be taking downhill steps. And that process becomes very small if your slope is so small, because then the gradient will be almost vanishing. And that is why people came up with something called ReLU, which we already discussed. It looks like this, the red curve here. And then ReLU solves a lot of this problem. Vanishing gradient problem doesn't happen in this region, but in this region, from x equal to 0 to anything that is negative in x, we will still have the vanishing gradient problem because there is no slope here. So that is why people came up with something else called leaky ReLU, which is slight, you have a tiny bit of slope here, and it's not entirely flat. So these are all different choices, and it is very hard to say beforehand what will work best for your problem and your network. So this is the choice of activation function is also a hyperparameter that people often try different functions, and then they try to see which one is working best for them and pick that one. Now, using a nonlinear activation function is a very essential part for neural network, and basically neural network is able to learn interesting features from the input x, and that happens using the nonlinearity of the activation. And this you can easily check by removing the nonlinear activation functions. If you just, let's say, replace your nonlinear function by an identity function, let's say gz equal to z. So no nonlinearity, just identity, then you will see that the neural network suddenly cannot perform well at all. So all the power that it had is now lost. So the nonlinearity is very important. Okay, now moving on to this back propagation step. So this is something we discussed already in the context of logistic regression. For neural network, you will just have the same backward arrows, but now twice, because you have now 2 layers. Just to mention one thing here is that random initialization is needed, it's necessary for W weights, W parameters for neural network. It is not necessary for logistic regression. You can just put W equal to 0, that will work. But here 0 won't work. You should have random initialization. Because 0 doesn't work, because then you don't have only one W, you have multiple Ws here. it's a matrix, and if all of them are 0, then all the hidden units basically becomes the same. They learn the same thing. They're not able to learn different things. So what we generally do is we use small but random values. Large values is a problem because you will use W to eventually compute Z. So if W is large, Z can be large, and Z being large would mean you will be pushing your gradient descent to operate in this asymptotic region, which will have the vanishing gradient issues. So keep W random but small. So generally this is how we do it. We use this NumPy random system and then multiply with a small value. B, however, can be initialized to 0. That doesn't create any problem as long as W is random. Okay, so now we are ready to look into deeper neural networks. So we started from here. This is a logistic regression and the simplest possible neural net. It's not exactly a net, it is just a neuron. And then we discussed one hidden layer neural network. So input, one hidden layer, output layer. This is with two hidden layers, input, one hidden layer, two hidden layer, output layer, and this is 5 hidden layers. So this is something we can call a deep neural network. So notations are important because as we are increasing the number of hidden layers, we are essentially increasing the complexity of your network, which is also known as architecture. So that is why rediscussing the notations are important. So number of layers is generally denoted as L. In this case, it is 4. 1, 2, 3, 4. Output layer is computed and is taken as the number of layers, but layer 0 is not taken. And then number of units in a layer, that is denoted as N superscript L. And here N1 would be 5, N2 would be 5, N3 would be 3, and N4 would be 1. N0 is the layer input layer, that would be 3. And activation in layer L, that is denoted as A superscript L. And then, yeah, somebody was asking this question if we can go A2, A3. So obviously you can. So it's the exactly same computation in every layer. So if you say X as A0, then you can generalize this this pattern here as ZL equal to WL A L minus 1 plus BL, and then we apply some activation function on ZL. Activation function is also layer dependent because you can choose tan H for one layer, ReLU for another layer, leaky ReLU for another layer. So that is why G to the power G superscript L is written here. That gives you AL. And ultimately that will give you A4 in this case, which is your Y hat. So now, okay, moving on. For whatever we wrote in the last slide, that is for one training example, for multiple training example, so we will vectorize, which means just replace small z by capital Z and small a by capital A. And recall that we defined them like this. So we had this column vector, just stack them side by side, and that is what we mean by capital A and capital Z. So this is how we avoid the explicit for loop. So matrix dimension is one of the things where we get some errors when you will be actually implementing this, even when most of the libraries are available, and you will be not implementing forward propagation and back propagation by hand. You will be using the existing libraries. Even then, you still have to write down your inputs, and generally the most confusion comes from the matrix size, and this is where if you just draw your network that you are using, you can easily see what will be the dimension of different matrices that you are dealing with, which are Z matrices, A matrices, and W matrices, and all of its dimensions are known to you. You just have to make sure that in the code also, the shape that is returned by NumPy is actually matching with your expectation. And this is very nice idea to check it in multiple steps to make sure that you can implement it as a sanity check.
Hello.
Yes.
Does it mean that if I increase the complexity of the network, the performance will increase, or like it is problem specific? That different problem has some optimal complex network which works well for that case.
Yes, this is a very good question. Indeed, it will be dependent on the problem you have, the complexity of your problem itself, and very importantly, it will depend on how much data you have to train your network. If you have, let's say, 1 million training example to train your network, you can afford to use a very complex network. If you have, let's say, 10,000 data to train, then you probably cannot afford to have a very large complex network. So how exactly you will decide how many layers to choose and how many hidden units to choose in a layer? This is called hyperparameter tuning. Number of layers is a hyperparameter. Number of hidden units in each layer is also a hyperparameter, and these are the things that you can tune. And how to tune that is something I also plan to discuss. I'm running a little bit late, so I should speed up. But yes, this is a discussion that we will do. So, yes.
One more question, that if my data set is small, let's say what you have told 10,000, and I use more complex network, then like what kind of problem I can get? Like,
You can get an overfitting problem if you think of it in terms of just a simple fitting. If you have let's say a small amount of data which it looks like a polynomial fit will be good, and if you do a polynomial fit with a lot of parameters, then you tend to overfit the data. So the same kind of problem will happen. It will be more difficult to visualize because it's now multi-dimensional. But generally, too small data but too many parameters will lead to overfitting. Yeah, which will mean that in your training set, your network will perform extremely well, but it will not generalize very well whenever you will come up with the new examples. So in the training set, excellent performance. In testing set, very bad performance. This will be the symptom. Okay. So now moving on. Yes. So in this this complex looking neural network, you have many layers. So let's say for layer 1, you compute Z1, and the dimensions are written here. So this is something if you are writing from scratch, you can check if this is exactly what you are getting or not. And then for M training examples, if I go back and forth between these two slides for 1 and for M training examples, what you see is that Z1 goes from N1 one-dimensional matrix to N1 m-dimensional matrix, and similarly the other ones. W1 doesn't change because W1 is not dependent on how many training examples you have. It is dependent on the number of nodes that you have in that given layer and activation coming from the previous layer. Okay, so now just a summary of what we discussed so far. This is the one iteration of your forward propagation and back propagation. The upper boxes are for forward propagation. So you go from left to right and you keep computing A0, A0 is given to you, that is the X. You keep computing A1, A2, A3, etc. And then AL is your Y hat. Once you reach that point, you compute the loss, and then at that point, your backward propagation start, where you compute the derivative of the loss with respect to the parameters that you have in each layer. And then at the end of the backplot, you update your parameters by using this learning rate times this derivative, and this that we discussed before. This is one iteration, and you have to do it many iterations to finally minimize your loss function or cost function. So now just I think I have 10 minutes left. I will finish in like 10 minutes, so I will not go into the next topic that I had, but just we'll discuss this simple thing, that why deep neural network actually works so well. What actually is it doing? So let's say you have a face recognition problem. Generally, this kind of problems are dealt with CNN, which we haven't discussed yet. So, but you can also do it using a DNN, deep neural network. So what it learns actually is that in the first, second, this beginning layers, it might learn to just detect the edges. So where the contrast is changing, going from dark color to white color, so things like that. These are called edge detection. So this is actually in the beginning part, first few layers, learning to detect edges, and this you can say that it is learning some simple features. And it, while learning the simple features, it might also just focus on small areas of the image, because in order to learn how to detect edge, it doesn't have to look at this whole picture. It might just focus on small boxes. Then when it goes deeper, then it might be able to learn more complex features, like let's say second layer, maybe detecting parts of the faces, maybe it is trying to understand what is an eye and what is a nose and this kind of thing. And then the third layer or more deeper layer, maybe looking at the whole picture and trying to differentiate between different faces. So this is a general idea that whatever problem you have in hand, the problem will have some simple features and then some other features with more and more complex things in it. So the first it will learn the simple things, and then it will learn more complex things. That is why if you have more and more layers, it will able to extract the more complex features from your data set. If you stop at the second layer, then it might not be able to learn all the complexities that your data brings in. And this have been mentioned already a few times, the parameters and hyperparameters, but just to reiterate, W and B, these are your parameters. This is something you learn via the gradient descent step, while the hyperparameters would be things like learning rate alpha, number of iterations that you take while doing the gradient descent, number of hidden layers, number of hidden units in each layer, choice of activation function. These are your hyperparameters, and this will control or influence your parameters. And the best value of a hyperparameter in general will not be known to you in advance, and you might have to figure it out with some trial and error, and of course some guidance can be provided about it. Now, how to actually do that, and I think I'll stop after discussing this. How to do that is that generally, if you have a big data set, you generally divide it in three parts: training set, dev set, and test set. Dev is development set and test set. So As we already discussed that machine learning, applied machine learning is a very iterative process. You have some idea, you need to code it up to check the performance and iterate this. So that is why this three separate set is very important. So use the training set to train your neural network. And then you can use the depth set to check which network is performing best. For example, you choose different values of your hyperparameters. So these are the hyperparameters. You choose different values of that, and you check in the depth set what is its performance. And in the first few iterations of this, you might not be happy with your performance. So you keep changing your hyperparameter and keep checking its performance in the depth set. And then at some point, when you are fairly happy with the performance of your neural network, then you check the performance in a completely new test set, which was not used so far in training and checking. So this will give you a completely independent test or check how it is doing. So in modern era of big data, we really have, depending on what kind of problems you are working on, you might in some areas have millions of data. And if that is the case, if your data set is really so big, then the division can be 98% for training, 1% for dev, 1% for test. But if you are dealing with small amount of data, let's say a few thousand, then the rule of thumb that most people follow is that 60% for training, 20% for dev, 20% for test. In some cases, people do not have a test set. So they do not have three different sets. They only have two different sets. One is training and another is dev, or you can also call it test. So if you have only two sets, then it can be, let's say, 70%, 30%, this kind of, so you have 70% for training and then test or develop it using the rest of the 30%. Yes, so I think I can take some questions here. I could not reach the point that I thought I will reach. So tomorrow, before starting with the basics of CNN, I would have to go through some of the things which are still related to deep neural network, although they are also used in CNN, because CNN is just an advanced kind of network of DNN, and all the things that you are actually learning for DNN, all of them are also applicable for CNN. So you can start from here tomorrow, but if you have questions.
Hello, ma'am. Hello.
Hi.
So here,
Yes.
if I want to like test my thing and I take similar amount of data as the training to test, what will be the problem? Like let's say I have like totally 5 lakhs of data set, and let's say I 2.5 lakhs for training, and then some of them for validation and similar, like let's say 2.5 lakhs for testing. So what can be the problem? Because by testing we are like computing the significance, right? So here, what problem we can get if I take similar?
Right. So you were saying that if you allocate more examples to your dev set and test set, what will be the problem? So the problem will be that we generally try to keep more data for training, because more data means better performance of your network. If you are taking out a significant portion of your data from your training set, then essentially you will end up with a smaller training set, which can hurt your performance. Moreover, the question to ask here is that, do we really need such a huge amount of data for dev and test? Because the only thing that the dev and test set will do is to quickly tell you whether your network is generalizing well to new examples or not. For that, generally a few thousand of examples is fine. So generally, by running your dev or test on millions or few lakh is not really needed. You are just taking out important data from your training set, which is not helpful. So maximizing the amount of data in the training, that is the goal.
And one more question, that you mentioned that there is, if I have, let's say, high level features for like as my input layer of DNA, like you told that there should be low level features, right? As we can see here this photo, that the ages it is learning. So if I give high level features on the in the input layer, so it will not learn the generic features. That's the problem, right?
Not exactly. So there are a few things here. Let's say uh, you have a very complex problem in hand, but you do not have enough data. So if you do not have enough data, then you will not be able to use a very complex and very deep neural network with many layers. So in that case, it will be useful if you hand engineer your input variables that you are providing in a way that you have a human intuition of the problem that you have. If you could use a very deep network, then the network will be able to learn the intuition that a human has learned. But it is not, you are not able to use a very deep network because you are constrained by the amount of data. So in that case, it will be very useful if you already give the hand engineered and your human intuition high level features as an input. So it has already learned the high level features, and then it will try to extract more complex patterns from those high level features. That is not not a bad thing to do actually. To give high level features is not a bad idea.
And one more thing, that it is silly that if I use both, like let's say I have like sufficient amount of data so that I can go deep, and also I can construct high level feature, and so that I am giving the input as high level feature. So this is not something bad, right?
Exactly. This is not bad thing because after all, at the end of the day, we do not control what a network learns. And not only that, we also do not know how it learns, right? It is a multi-dimensional parameter space that we are not even able to draw. So we don't know what it is learning. So if you can make sure that what we as human already know about a problem, I transfer my intuition to the network, and then whatever I was not able to learn because the data is so complex, let the network figure that out. So I give both to the network, my human level intuition and this huge amount of data, and then let the network figure out the best from both.
So it's like that I can give, let's say, whatever I can, like in high energy physics, I'm telling that whatever complex function I can make from the generic features, and that I will give, and also the generic features that I have, that I will also give, because we don't know that what is learning, right?
Exactly, exactly.
Okay, okay, okay. Thank you.
Is there any other question?
I have a doubt on the gradient descent.
Yes.
In the gradient descent, we are taking the value y value at 0, 1 or y hat value at 0, 1.
Yeah.
If I for sigmoid function, if I take y value at 0, 1 and y hat value at 0, 1, But if I take y-hat value 0, 1, that function is undefined, that log 0.
What do you mean?
If I take y-hat value 0 or 1, then this function will be undefined.
Mm,
Y-hat is
Generally,
not 0, 1.
y-hat generally will give you a value which is between 0 and 1.
0, 1.
But generally it is something very close to 0. But generally it doesn't happen that it is exactly 0. Because what you are getting from here is a value which is very, very close to 0, which you are interpreting as something which is 0. Like it is a probability. If your network is saying that the probability of this photo being of a cat's picture is 0.001, then essentially it is telling you this is not a cat, right? So it means it is predicting it correctly or wrongly, whatever is the given picture. But the value being undefined never happens, because almost never happens, because it is giving you a value very close to 0. It's generally never exactly 0.
Okay.
Ma'am, in the cost function, is there, I mean, a possibility that we will have a local minima also? I mean, then our iteration can get stuck there. Is there some possibility like this?
Generally, one of the reason this I did not discuss, but yeah, there was a question asked why this value, this particular expression is taken for loss. So this is another reason that this was found to be a very well-behaved function, which does not give that kind of feature that you were telling, that we have multiple local minima. So this generally doesn't happen. Also, we are looking at it from a two-dimensional point of view, just to understand, but in reality, it is a multi-dimensional, very high-dimensional space. And it is very unlikely that even if there is a local maxima or local minima, the probability to actually becoming stuck there is actually very low. I will not say that it never happens, but it is with this particular form of cost function, and also by the fact that this is such a high dimensional problem, that probability is very negligible.
Okay, ma'am.
Okay, any other question? Okay, seems like not. So, Arun, is still there?
Hi, Swagata. Yes, I'm there. So I think if it's over, then we can stop now. So we continue tomorrow.
Yes, I think I see a chat. Any reference can you suggest? Yes, I have some reference. I will mention that tomorrow at the end of my lecture.
So there is one reference which is
Sorry, Arun, I didn't catch that.
wait a minute, just I find it. Trevor Husty, elements of statistical learning. I can post it. Wait a minute. Yeah. In fact, this book is available online for students. I find this book very, very good.
Yes, yes, indeed. This book is very good. Yeah. Can you please also share the slides? Yes, I wasn't sure until what point I will reach today. That's why I didn't upload. I will send my slides to Arun, and maybe Arun, you can upload it to this.